Keivan Mallahi-Karai. And again, as I said, for every speaker there is a very special reason for him to be speaking today in honor of Alan. And in this case, Keivan is probably the closest from the faculty here to Alan. They talk a lot, they're very good friends, and they discuss a lot of mathematics, and I'm happy to.
Thank you.
All right, thank you very much, Ivan, for this very nice introduction. All right, so let me just also start by saying maybe a couple of words about somehow the way I got to know Alan and what I really appreciate actually about sort of our collegiality and our friendship in the last I think about 10 years. Yeah, almost 10 years. So I got to know Alan when he came to JUB. So Ivan mentioned this morning that Alan joined JUB's faculty in 2009, and so we started. I think Ivan introduced us for the first time, and we had a very brief chat. And then somehow, I think maybe after a couple of years, so I think Alan was around for a while, and then we started really talking much more. And yeah, so I think a couple of things which I can say very clearly about Alan is that, well, number one, sort of on a more mathematical level, I think I would like to just reiterate what Alan said this morning, that Alan is somebody who is genuinely interested in mathematics. And it's not, this kind of mathematics or that kind of mathematics, it's just mathematics. And I think our fields of interest are not necessarily, they're not 100% overlapping, but we managed to have a lot of interesting conversations. I personally learned a lot of mathematics from Alan, so the area of mathematics that I'm coming from, complex numbers do not have any particular status. They're just essentially, an extension of real numbers, even too. So you just treat them like any other field. But I did learn a lot of complex analysis from Alan, and a lot. Really like how do you think about them, and how do you think about complex geometry and so on. And on a more personal level, I would say that Alan, for me, is just a kind of super optimistic person. Just sees positive things in almost any situation. So, sometimes we talk about some, one student who's not doing so well. This is a very good way of putting it. Like, sort of, if you want to put it very, euphemistically, you would say. Yeah, I know. I'm not going to mention any names, but kind of, when you talk to Alan about cases of this sort, he sees more or less, doesn't necessarily talk about where the student is, but talk about the derivative or even the second derivative, So when somebody's getting better, this is what is emphasized for Alan. So this is something that, again, I've learned from him, and I think, I think it's one of those characteristics that is extremely positive and extremely.
What is second derivative? First derivative is getting better, second is right.
Yeah, they're not getting better, but they're not getting too bad too fast. So, yeah. Anyway, so what I'm going to talk about today is not. I tried to sort of prepare the talk because I know it's a very heterogeneous audience, and this talk per se is not. It's something that I talked to Alan about, so you probably know more or less everything which is in this talk, but. So it's not necessarily the center of of this conference. So it's not exactly related to probably the research interests of many people in this room. So I tried to make it sort of rather broad, and also there are a number of students here. So I tried to make it also there at least there should be at least one thing in this talk that I think all the that everyone in the audience should understand. So anyways, so the setup. I'll just start maybe by recalling the setup. So we are going to be interested in a notion which is called the faithful dimension for finite groups. So this talk is going to be mostly about finite groups, but there will be a lot of other things that that will come in. So the faithful dimension, I don't know what happened here. Let me see. up to what is okay. Can you have the maybe I can talk to you. Oh, okay. Thank you. Maybe the other way around. So sitting in front is 2. Oh. Okay, well, this is better probably. And I can probably look at myself as well. Alright, good. So I think this is good. So the setup is the following. So G is going to be a finite group. K is a field, dimension is going to be the field of complex numbers. And what we're interested in is, well, by definition, a faithful representation of the group G over K is a way of embedding a group argument group G into the group n by matrices over the field K, and the number n is called the dimension of this representation. Okay, so this is kind of a standard terminology. I think a lot of people probably are familiar with it. And there's a simple fact, so I promise to, to say something that everybody understands, and maybe I'll prove it as well. So there's at least one proof in the talk. So there's a simple fact that every finite group is going to be embeddable inside G and K for every K and every n. Okay? This is one of those facts that, I think it might be impressive to you before you actually see the proof. So the proof is very simple. The proof essentially uses the fact that if you have any group, you can realize this group as the group of permutations of a set. So if you have a finite group, it always it acts on itself, and that gives you your group can be embedded as a subgroup of the group of permutations of a finite set. And of course, the group of permutations of a finite set is embeddable inside the group of n by matrices by means of permutation representations. So permutation matrices. So this gives basically the proof for this very simple fact. And what we're interested in is what we call the faithful dimension of the group, which is the smallest dimension of a faithful representation of a group G. So you fix the field K and you fix G, and what we're really interested in is the smallest dimensional representation where you can get such a faithful representation. Alright, so the argument which I just gave you essentially shows that this number is always bounded from above by the size of the group. This is essentially coming from the regular representation of the group. And one reason that this number is interesting, I mean, you might be interested in this number for its own sake, but one other reason that this number has been of interest is due to its connection to another notion which is called the essential dimension. So this notion was introduced by Buller and Reichstein in 1997. So again, there is a notion of essential dimension for a lot of mathematical objects, and in particular for groups. This was sort of worked out by Buller and Reichstein. And this number, I will mention the definition in the next slide, but I will just point out at this point that this number is always lower bounded with a faithful dimension of the group. And one good situation, which I would like to emphasize for this talk, at least it might be important, is that in the case that the group is a P group, so this means that the size of the group is a power of the prime P, and K is a sufficiently large field, so for instance, if the field of complex numbers, there is a theorem of Karpenko and Merkuriev which says that these two numbers are in fact equal. Okay, so the essential dimension actually coincides with the field. So now, what is this essential dimension? So the definition is the following. So suppose you have a finite group G and you have an algebraic variety X, and suppose G acts on X. So this action is called faithful if the embedding from G to the group of automorphisms of your algebraic variety is injected. And then you have the following definition that if you have so suppose that you have a faithful G variety, then the essential dimension of this X is the minimal dimension of a faithful G variety that you get as a dominant image of X. Okay, so you basically try to start with this algebraic variety of which G acts faithfully, and then you want to sort of compress it to the smallest possible dimension so that the action is still going to be faithful, and the smallest dimension of such a thing is called the faithful dimension. And then Buller and Reichstein, they proved that this number actually doesn't really depend on the variety X that you start with. What it really depends on is the group G. Okay, so you start with a group G and you let it act on any variety by automorphisms, algebraic automorphisms, and then you try to find the smallest dimensional variety that you can get as a quotient, so to speak, or you need basically the dominant map from your variety X to this other variety Y, and this smallest number is called the, it's something which only depends on the group G and not on the choice of the variety that you have.
Could you remind us what was the dominant?
So it just means that roughly speaking, you can see that it's like a surject, the derivative should be surjected essentially. This way you can figure that. Alright, so now we want to go to the group side. So the first example of a group that I want to mention is a group that I think a lot of people in this audience probably are familiar with. This is called the Heisenberg group. So there is something here which I don't want to, don't look at them. So let me just show you what the Heisenberg group is, because I think if there is one group that maybe everybody in this audience should at least take away from this talk, is the Heisenberg group. So the Heisenberg group over any ring, so let's say here I put K, or 2K plus 1 in my notation. So it's basically the group that is a group of K plus 2 by K plus 2 matrices that you can get by looking at matrices of this form. So every place where I put stars, you're allowed to put elements of the ring, and in other places you need to have 0. Okay? And the group operation is just a group multiplication. So this is called the Heisenberg group. You can sort of look at it as what is called a group scheme, in the sense that you can plug in your favorite ring here, and that is going to produce a group for you. And so somehow that the result, which is written down here, is a precursor of the works that I'm going to talk about today. So in some work, I think it was in 2016, appeared. So in joint work with several colleagues in Canada, we computed the faithful dimension of the Heisenberg group for a particular class of rings. So these are rings that, so the definition is very complicated, but the way you really think about them is the following. So you have finite fields, and you also have rings like Z mod P and Z. Okay? So for every prime P, so if P is a prime number, you have the ring of integers mod out by P and Z. So this is a ring which you can construct from Z by modding out by some power of prime. So you have a similar construction in which you can replace this Z by slightly more general rings. Okay, so it doesn't matter what they are, but let's not worry about this. But anyway, for this type of rings, we actually managed to compute the faithful dimension. And as you can see basically from this formula, what you get as a result is a polynomial in Q. Okay, Q is just the power of P that shows up here. So Q is P to the n, basically. And this was somehow, at the beginning when we proved this, it was not so important for us. It came basically from a different, we got into this project somehow, from a different direction. But so we proved this. And then later, it became sort of interesting to us to understand this number for other types of groups that are basically similar to the Heisenberg group. So what do I mean by this? So suppose that you have a group which is constructed in a similar fashion. So you have something like a group scheme, and you want to plug in a finite field into this group scheme to produce a group for you. Okay, so in a similar way that you have, let's say, this group scheme, and then we can plug in SP here, and that will give you a group, which is a group of Heisenberg group over the finite field SP. And then the question you can ask is it reasonable that the dimension of the faithful dimension of the group that you get is a polynomial in P? Okay? Now, why is it a reasonable question to ask? So maybe I should say a couple of words about somehow the basics of representation theory. Everything? Yeah, okay. So, just to make this a little bit more, sort of, to make the question a little bit more, oops, did it disappear or not? Alright, so I hope it comes back. So, anyways, so just a couple of words about representation theory of finite groups. So, if you have a group G, so a representation of G, as I said at the very beginning, is just a map from G to the group of. So let's say you're just talking about the complex representation. So it's basically group homomorphism from G to G elements. Now, there's a very old theory of this theory is extremely old, goes back to people like Frobenius, Schur, etc. at the beginning of the 20th century, who understood basically the representation theory of finite groups. So it turns out that if you have a finite group, any representation of this group is going to decompose into a direct sum of the so-called irreducible representations. And one fact, which is particularly useful in the case of the P groups, is that the dimension of every representation divides the size of the group. So if you have any representation, any irreducible representation, the dimension of this representation is always a factor of the cardinality of G. So if your group has cardinality, let's say, p to some power, then any irreducible representation is going to have dimension p to some power. Okay, so this is a simple fact. And then, if you have a group G, then, well, if you want to construct a faithful representation of your group, you have to construct it by piecing together irreducible representations, so that although each one of them has a kernel, the intersection of the kernels is a trivial sum. Okay, so the direct sum does not have any kernel. So if each one of them has dimension p to some power, then it's quite reasonable that the representation that we're going to construct also has dimension p to some polynomial in p. Well, this looks like I already answered my question, but it's a little more subtle than this because the way you want to construct this representation for every prime key could be different, right? I mean, for every prime key, you have to piece together different representations, and the question is whether you can actually do this in a uniform fashion for all of these groups at the same time. So, anyways, so this is the question that I call the polynomiality question. Suppose you have a family of groups, which is naturally parameterized by a prime key, and then the question is, does there exist a polynomial with integer coefficients so that the faithful dimension of this group scheme, or this group over a finite field with p elements, is given by a polynomial, by that polynomial in P. So let me try to formulate this problem a little bit more precisely, because I didn't yet tell you exactly how these groups depend on the parameter P. So in the case of P groups, there is in fact a very nice construction, which is called the Lazare correspondence. I think it was done in the 70s by Lazare, which relates finite P groups to finite Lie algebras over rings with power prime number of elements. So I'll just try to briefly explain what this is. So suppose that we have a finite Lie algebra over Z. This cardinality is the power of prime P. This is not good. Something right there or not?
So this finite.
Yeah, so suppose you have a finite Lie algebra.
And Z module, finite Z module, which is a zero.
Yeah, I mean finite Z module, which is a Lie algebra. So if you take this a Heisenberg group, for instance, or a finite ring or a finite field with P elements, so some power of P elements. And suppose that in the equivalency class is, well, P should be large basically for this construction to work, so P should be bigger than the equivalency class. And then you can define an operation. It doesn't matter so much what this formula is. So this is a formula which is the truncated version of the so-called Campbell-Baker-Hausdorff formula, which tells you how to write in an equivalent group. So suppose you have an equivalent group like a Heisenberg group or a field of real numbers and complex numbers. And then you want to write the group multiplication, this is the standard visual formula using the exponential map in terms of the Lie algebra. Well, this you can do, and if you truncate it, so this of course requires convergence, you can do it over R or C, but if you want to do it over finite ring, you can still do it because the commutators after some point are going to go to 0. Okay, so if your Lie algebra is important, you can, this stops at some point. And it turns out that this operation, which is defined in this way, really defines a group. Okay? So the Lazare correspondence is precisely the fact that you can also reverse this process. So if you have a finite group with number of elements in power p, this group is coming from a Lie algebra by means of this construction. So there are two, I mean, this formula was just too complicated, but I just want to show you two special cases which may be a little bit more familiar. So for instance, if an equivalency class is 2, then this formula just simplifies to x plus y plus a half of the commutator. And for the equivalency class 3, again, as you can see, you have commutators and commutators of commutators, but you don't have commutators of longer, so longer commutators just, they get cancelled essentially. So for this construction, again, to work, as you can see, the denominators should be well defined. So for that reason, you need the characteristics to be large in comparison to C. Yes?
This restriction on an equivalency class on the side of Lie algebra, and do you have any similar restriction on the side of your P group?
No, there's no. You mean? You mean whether P should be bigger than C? The
So
same kind of.
This relation would be automatically satisfied.
Yeah, this condition you need on both sides. I mean, for this to work. All right, and then Lazare says that basically this group, which is defined in this fashion, is always going to be a P group of class C. And if you have a P group of class C and P is larger than C, then it's arising in this fashion from a unique Lie algebra. All right, so in this way, we can actually formulate the problem that I stated at the beginning rather vaguely. We can formulate it more precisely. So the way we're going to do it is that we're going to start with the Lie algebra, which is defined over Z. And then you can construct the Lie algebra over, let's say, a finite field SP by just tensoring your Lie algebra. And then apply the X. So X is just the operation which you define. So it's the group which is associated to this finite Lie algebra. And this gives you a group. Okay? Another question, so this polynomiality problem, which now can be stated in a precise way. So is this map which assigns to every prime number the faithful dimension of the associated group? Is this a polynomial in P? Well, somehow what happened is that, as I told you, we were interested in the Heisenberg group at the beginning, and we started thinking about this problem. And our initial idea or way of thinking was that this should be probably the same. So the answer to this should be positive. And it should not be too hard. I mean, we had roughly a sketch of what we should do. What happened at the end was that we discovered, first we thought that we had actually proven what we thought was true. But then it turned out that in fact the truth is much more interesting than what we were hoping it to be. And I want to start by maybe giving a number of examples of situations in which the function is not polynomial, and then try to explain what is true. Okay, so the first example is this Lie algebra, 9-dimensional Lie algebra. So I have to tell you exactly what these notations mean. So in the Lie algebra with the basis we want to be 9, so we just fix, let's say, a finite field, that's a field of scalars. And any commutator which I did not write down here is equal to 0. So in order to specify the Lie algebra, I have to tell you exactly what the commutator of basis elements are. Well, okay, except the ones which are, the ones that are obviously, let's say, B5 and B1 minus B8, etc. But the commutators that do not immediately follow from any one of these are equal to 0. So this is a two-step Newtonian Lie algebra, which depends on this parameter A. And for this Lie algebra, the answer to that question is yes. So the faithful dimension is given by a polynomial in prime P, namely 3 times P squared. But this fact is not an obvious fact in the sense that this is much more complicated than the case of Heisenberg group. So I'll come back to this later in the talk. So the reason that this is true is basically has to do with the fact that if you look at this elliptic curve, which is defined over Z, for any sufficiently large prime P, this elliptic curve has a non-trivial point. Okay? And let me just add one more point here, that this fact is not because this elliptic curve you can show does not have any non-trivial integer point. Okay, there are some trivial points like if x is 0, then y is 0, etc. But you can show using something which is called Hasselbound, which counts the number of the points on an elliptic curve up to some error. That there are a lot of points on this elliptic curve for any prime p, but these solutions do not come from any solution which is sort of globally defined over C. So for every prime we have a new solution, but these solutions have not.
Where does the cubic, how does this cubic equation arise?
I'll show you.
No.
I'll explain. Okay, here's the second example. So this is already interesting. So the smaller the algebra, so 6 of dimension 6. These are the commutator relations. And the faithful dimension in this case is given by 2 different polynomials, depending on whether p is in the congruence class of 1 modulo 4 or the congruence class of 3 modulo 4. So this is already the first example which shows you that things can be a little bit more complicated. And here's the third example, which is even more complicated. And in this case, again, you get 3 different polynomials. But this time, they are not even defined by congruence classes. So, so they have 3 different polynomials, this one, this one, this one. And there are 3 different conditions on the prime p. Let me just explain what this notation means. So this notation means that p, if you look at it modulo 23, it's not a perfect square. So if you look at the image of p in Z23 or F23, it's not a perfect square. So it's called the Legendre symbol. And if it is a perfect square, then there's a theorem, which is a non-trivial theorem, that your prime would be representable by one of these quadratic forms. And depending on which one, you're going to get one of these 2 polynomials. Okay? So, there's a lot of number theory sort of lurking behind this picture, and this is basically what we started to see after some point. So, let me try to explain maybe the first results that can be proven here. So, in order to state this result, I need to define the notion of a Frobenius set. So, suppose you have a polynomial with integer coefficients, and then we can define the following set, which is a subset of the set of prime numbers. And this consists of the set of primes for which, if you reduce this polynomial modulo p, that polynomial has a solution over Fp. Okay? So you start with an integer polynomial. So there are some people from my number theory class. So you start with a polynomial which is defined over C. You reduce it modulo p, you get a polynomial over Fp. And depending on what p is, this may or may not have a solution. So you're just collecting all of those prime numbers for which this does have a solution. This is called an elementary Frobenius set. Okay? So for instance, if you take the polynomial to be, let's say, t squared plus 1, the set of primes for which this does have a solution inside Fp, well, these are just 2 and all the primes are the form 4k plus 1. Okay? So the one that are congruent to 1 modulo 4. This is an example of a Frobenius set. Of an elementary Frobenius set. And a Frobenius set is precisely a set which can be written down or expressed as a Boolean combination of elementary Frobenius sets. So essentially what you are asking for is that certain polynomials do have a solution when you reduce the modulo p, and certain polynomials do not have a solution. So the first theorem, so this theorem is a 1 year old, and it appeared just a few months ago. Is the following statement that if you start with an equivalent, the algebra over Z of the equivalency class C, and then the statement is that you have a partition of the set of prime numbers into Frobenius sets, and you have also a family of polynomials, a finite number of polynomials with integer coefficients, so that depending on which one of these Frobenius sets contains your prime p, that polynomial, the associated polynomial, is going to give you the faithful dimension of the associated. Okay? So essentially what proved was that your, so the faithful dimension as a function of p is a piecewise polynomial function, and the domain of each one of the pieces is a Frobenius set. Okay? So this is somehow, I think a couple of examples which I gave below maybe would suggest something like this. So I'll say a couple of words about how this thing is proven. Let me mention also a different direction that you can also ask these questions. So this time you are going to fix the prime p, and then instead of going over the set of all different primes, you look at the powers of this prime p. So again, you're looking at, so let me just write it down here. So you're looking at f p to the f. So you're looking at all the primes, all the algebra over Z. You tensor it with this field, and then you're looking at the associated group, and it's called this G e to the F, right? So it's a similar construction, but instead of varying primes, you're fixing one prime and going sort of over the tower of the powers of this prime. And this time we also have a similar statement. So again, we have a finite number of polynomials, and we also have a partition of the set of natural numbers into sets, each one of which is a union of finite set and finitely many arithmetic progressions. And this time, depending on which one of these sets contains F, you're going to get one polynomial. Okay, so this again is some sort of uniformity theorem, but instead of moving the prime, you're fixing one prime and going over the tower of powers of this prime. Alright, so the machinery which is at the back of most of these results is something which is called Kirillov's orbit method. So this is something that I guess probably more people in this audience are familiar with. So I'm not going to explain this, of course. It's a very useful machinery, so I think a lot of us who are sort of, I'm not really coming from the world of finite P groups, but, for a lot of interesting groups that most of us probably deal with, representations, they all come from some sort of geometric construction. So if you, let's say you look at SL2, over anything, over C or over, let's say, finite fields, implicit representations of these groups, they can be constructed somehow using objects that exist independent of SL2. This is somehow along the same line that of Ivan's talk this morning. For P groups, the situation is completely different. So these groups, so Kirillov's orbit method somehow allows you to construct or to parameterize the implicit representations of Newtonian groups, and in this case, this would be for P groups. But this is not in terms of objects that somehow exist independent of the P group, but these are objects that you can construct using the P group itself. Okay? So in some sense, it's, to me at least, it's still kind of a surprise that you can actually have such a nice parameterization of all the implicit representations of a group which is so flexible. So this is something, again, that after you start working with Newtonian groups or P groups, you realize that they are much less rigid than things like semi-simple groups that are much more familiar somehow. So anyways, so what is the construction? So suppose that you have a finite P group. So this is Kirillov's orbit method, not the classical one, of course. So the classical Kirillov's orbit method was basically developed to understand the implicit representations of Newtonian Lie groups. This is a modification of Kirillov's orbit method, which works for finite P groups. But somehow the method is very similar. So we start with P group, which has an equivalency class of length P. You look at the associated Lie algebra according to the Lazar's correspondence, and you can define the coadjoint action of the group G on the space of the hump of G and C stars. So this is the coadjoint representation. And then you can define this action. So the action is the following. So if you have theta inside the dual of G, and you have some element coming from G, so you're basically viewing G as the group itself. Okay, so you're putting the group operation of the Lie algebra, identifying essentially the group with the Lie algebra. Then the action is given by this formula. And what is important for us is not exactly what the action is, but the following formula. So you can see this is a formula that tells you if we start with some G orbits inside G hat, which corresponds to some representation of the group G, then the dimension of this representation is given by the so-called Kirillov's character formula, which is the following. So it's size of theta. This is the orbit that corresponds to your representation. And then here you're just averaging theta over the full orbit. Okay? So this formula is extremely useful for us because it tells you, we're dealing with the dimension of some representation, and the dimension of representation is essentially a character evaluating that identity. So once you know this formula, you can actually compute the dimension of any faithful representation simply by knowing where it really comes from in this correspondence. Alright, so this thing has been, as I told you, Kirillov basically developed this theory for dealing with or characterizing in some sense implicit representations of Newtonian Lie groups. Roger Howe extended this to p-adic analytic groups and finite generated Newtonian groups. So this is some, I think it's a very old work of Roger Howe, and then some other version of it was proved by David Kojdal. And more recently, this was also used in a number of different works for understanding something called a representation zeta function for different classes of people. So it's a tool which has been used actually before this work, and it has been extremely effective in sort of dealing with irreducible representations of finite groups. So let me just explain what are the ingredients of the two theorems which I just stated. So one tool that we're using is a factor model theory, so this is called Axe theorem. This is how you are basically how we are relating this set of primes for which each one of these polynomials is going to be working to the Frobenius sets. Okay, so there's a theorem which is Axe theorem. I'm not going to state it, but this theorem basically provides this partition into Frobenius sets for us. And then, as I told you, so the Kirillov machinery is going to be in the background, so we kind of represent these representations that come in the construction, they come through this Kirillov machinery. And then one other ingredient, which is somehow related to the question Alan asked a little bit earlier, is that in order to effectively use this Kirillov machinery, we need to somehow parameterize the irreducible representations that we would like to have in our representation rho in a very nice form. So this again has been used, I mean there was other works before, there were other works before that did something, I mean they needed to deal with similar kind of problem, and they used something which is called the commutator matrix, which you can associate to this independent Lie algebra. So let me just explain this, maybe on the chalkboard I'll explain this, because I don't think I have it here. So what we do is that you have to look at your Lie algebra G, and then you look at G mod the center of G. So here you can basically, let's say, span it by a number of vectors, V1 to Vk. And then we can define the following matrix. So here I'm going to write, let's say, the rows and the columns of this matrix are enumerated by V1 to Vk. Okay? And then I compute the commutator of each mu I and Vj, and I write it down as a linear combination of, let's say, a different basis for the commutator subalgebra of G. So this is also spanned by, let's say, W1 to Wn. Right? So I fixed these two bases. So this is basis for G mod the center, and this is basis for the commutator algebra. So I can compute each one of the commutators, and then I can express it as a linear combination of W1 to Wl. And this is going to give me a matrix. So this is going to be a matrix. So let's say, here I have some linear combination of, let's say, some W1 plus something W2, etc. And what basically characterizes at the end, so maybe just, I think it might be on the next slide. So what we do is that we reduce our problem to the following optimization problem. So the matrix that is defined here, it doesn't matter what it is, but this matrix defines a number of so-called rank varieties. So these are the varieties which are defined by means of setting the rank of this matrix to be less than or equal to something. Okay, so you have this matrix, and let's say each attribute of the matrix is going to be a linear combination of some variables. And then we say, well, if I want this matrix to have rank equals 2, what are the equations that should be satisfied? So you have to set every 2 by 2, every 4 by 4 determinant. It's a skew-symmetric matrix, so you need to set every 4 by 4 matrix, submatrix or minor of this matrix to have determinant 0. So this defines something which is called the rank variety. And the question is, does this rank variety have points over a finite field of interest for you? So this formula tells you that the faithful dimension of your group over the finite field Fq is given by the following sum. And so let me just explain what this is. So here, this matrix Fg is your commutator matrix. And what you would like to do, intuitively speaking, the formula itself doesn't really matter at this point, but what you really want to do is to find enough points on these rank varieties that are linearly independent. Okay? So again, going back to the beginning of the talk, what you really want to construct, an irreducible representation. So this representation has to be built out of, you want to construct a faithful representation, which has to be built out of these irreducible components. Each irreducible component comes via this Kirillov machinery from some coadjuvant orbit. And what we would like to do is that the kernel of these irreducible representations do not intersect anywhere. So the last condition essentially comes from this matrix being non-singular. This is essentially the condition that tells you that the intersection of the kernels of these irreducible representations is trivial. And the number that appears here is essentially the sum of the dimensions of those representations. Okay? And if you want to have a representation which has small dimension, this representation should come from a point on the coadjuvant orbit, and whose size is small, and the size of the coadjuvant orbit is given exactly by something which has to do with this rank variety. Alright, so, okay, maybe I should kind of go a little bit faster. So, this was basically the general picture. So if you have a family of groups which are coming from one Newtonian Lie algebra, this is the statement that you can make, and you cannot make anything better than this, as I showed you at the beginning. Now, it turns out that there are some interesting families of Lie algebras for which you can prove better results. So one family, which by the way I was not personally really interested in and never thought of it as being particularly interesting before, are the so-called root groups. So these are the groups that can be defined in the following way. So you start with the partial order of the set 1 to n, and then you're looking at the Lie algebra, which is called the root Lie algebra, which is basically the span of those elementary matrices for which I is less than j in your partial order. Okay? So for instance, if your partial order is just the full order, so 1 is less than 2, less than 3, up to less than n, you're going to get the full upper triangular group. But there are other partial orders that would create for you the Heisenberg group. And in general, if you start with any partial order, this is going to define a group for you. So these are called the root groups, or pattern groups. In the literature, sometimes they're called pattern groups. And for the case of these groups, there are some combinatorial data that you can define. So this, I don't want to go through all of them, but let's say if you have two numbers I and j, and you can look at the number of k's which are between I and j, so this is some combinatorial information that you can read off of your partial order. An order pair ij, you call it an extreme pair if they're comparable, and I is minimal and j is a maximal element in this partial order set. And then it turns out that the faithful dimension in this particular case can be given by a single polynomial in P. Okay? Or if you're working over powers of primes, it's given by a single polynomial in Q. And as you can see, this number, this polynomial, you can actually write it down as soon as you know the Lie algebra. This generalizes, by the way, the result that we have for the Heisenberg group, because the Heisenberg group is an example of a group which comes from this partial order, so it's a root group, so to speak. And for any root group, you can get this polynomial as soon as you have this combinatorial data. As a particular application, this theorem also shows that if we start from any polynomial, you can construct a Newtonian Lie algebra for which the faithful dimension of the associated group is given precisely by that given polynomial. So any polynomial can arise in this fashion. So this is, okay, so I think there are a number of students here present. I just intentionally picked this lemma. So this relies on a lot of different things. So there are some combinatorial ideas in this proof. But there is one lemma in the proof which we somehow didn't know. I mean, we just sort of discovered essentially by chance. And we needed it in the course of this proof. And it's, I think, an interesting lemma. It's a combinatorial, it has a linear algebraic flavor, but in fact there is combinatorics behind it. So you can replace, if you don't like finite fields, you can replace fq by c, and you can replace fp with r, and replace m or s by 2. Okay? So let me tell you exactly which lemma says in case of c and r. So suppose you have a vector space of dimension m over c, and suppose you have a number. So you can of course look at this as also as a representation by means of restriction of scalars as a vector space over R. Okay? Now suppose that which has dimension 2 times n. Okay. Now suppose that I give you a basis for this vector space, which has size 2 times n. Then this number tells you that you can divide this basis into 2 sets, each one of size n, so that each one of them is a basis for the initial vector space as a vector space over C. Okay? So this is, it's a subtle fact, and in fact it's not true that you can do it completely arbitrarily. So you have to be very careful in how you're basically dividing these spaces into 2 subsets of size n. And the proof uses some combinatorial ideas like Philipp's theorem and so on. But anyway, so you can actually prove this, and this is one of the ingredients in the proof of the previous lecture. There is yet another example of family of Newtonian algebras for which you also get a uniform formula for all the primes p. So these are called the free Newtonian Lie algebras. So these are the Newtonian Lie algebras that you get essentially by taking the free Lie algebra and a certain number of generators and then modding out all the basically a certain element in the lower central series. So you're setting all the commutators of a certain length to be equal to 0. So these are called the free Newtonian Lie algebra. So essentially this is the largest Newtonian Lie algebra, which is of Newtonian class C. So for these, we can also compute this faithful dimension. So if you look at this tensor with Fp again and look at the group which is associated, you get a finite P group. And you can actually compute, as you can see, in this case, this rank variety has enough points already for rank equal to 1. And that's why the answer is just the
Are these minimal representations somehow distinguished? I mean, you see them in some other way as distinguished representations?
I mean, so you see, these representations, I mean, they come from, this is n squared minus n divided by 2 representations of dimension p. So you have to, I mean, somehow, construct a representation of dimension p. You don't really see them, and I was telling you, I mean, at least we don't see them. So, for Newtonian equals, I mean, I at least don't know any other way, independent of looking at this quadrant orbit of seeing these representations. I mean, I think already for Heisenberg, maybe we can see somehow. Even there, I think it's not really, you don't see it as an action on anything, like projecting. There's nothing like projecting.
So this is associated to an orbit.
It's associated to some orbit, exactly.
Well, but there is a fine polarization for it, and I find it quite good in this case.
Hmm?
You can try to guess a polarization for this orbit, and it can be quite good in this case.
Well, I don't know what you might call it good, but I mean, it comes from some, you find some points in this rank variety, and they correspond to some quadrant orbit, which corresponds to some representation. You can track this and you can write down this representation, but at least I don't see anything which is as good as, let's say, projective line, like for active representation of SL2. If that's the kind of thing you're looking for, we don't see anything of that sort, and I doubt that there is anything of that sort, but maybe there is. I mean, I suspect that there might be some algebraic geometry behind all of this, but we haven't yet managed to see. If there is anything, we haven't yet seen that. Anyway, so I think I have maybe a little time left. So these are some other computations in small dimensions. So for the equality class up to 6, we have also computed these numbers. As you can see, again, you get some polynomials. We did it somehow by hand, and it doesn't suggest even a pattern. It's sort of interesting what's going on here, but we don't know. We don't even have a conjecture in this case. So there is another class of groups for which you can actually compute. So this is work that I'm doing now with one of the master students here, Dimitri Gonzalo. So these are the groups, so they're called free Newtonian Newtonian Lie algebras of Newtonian class C. So this is basically the Newtonian Lie algebra that you get by modding out the second derived subgroup and also the C subgroup in the lower central series. So this is some of the largest Newtonian Lie algebra of Newtonian class C. And for these, we can also compute exactly the faithful dimension. So this is a very combinatorial proof again. So, I have talked to a number of people, sort of algebraic geometers, just to see if these varieties that somehow show up in this construction, if these are varieties that are known to people. But so far, I haven't been successful. So maybe they are. Maybe there is a better way of seeing where these points actually come from. But so far, we just construct them by I would call them combinatorial means. Somebody just constructing by hand, and you will find enough points which are linearly independent, and that's the way it works. So anyway, so I think I might just say a couple of words about this. I think I already told you that the proof, at least for the last result, essentially relies on combinatorial arguments and constructing these points by hand, but it is not completely unlikely, actually, to me. In one case, the special case of this, which we did in our paper before the work with Dima, so one of these cases, we actually, the variety that arises is this variety that, T goes to, what essentially makes this work, this variety we probably have seen, that, if you pick, let's say, a field, and if you pick, let's say, points alpha 1 to alpha, I believe, n, so let's call this phi. So phi of alpha 1 to phi of alpha n, if they are visually distinct, these points are in general position. So something like this, is in every situation like this, you need to come up with a statement of these points. So you need to come up with a lot of points which are not belonging to any, there's no hyperplane basically that goes through all of them. And so this makes me think that maybe there is something going on behind it, but at least so far I don't know. Okay, so I think I might be running 5 minutes left, but I think I'm going to just stop now. Okay, thank you very much.
So, comments, questions? Okay. Thank you.